In this video, we're going to go over acids and bases, particularly the Arrhenius definition, the Bronsted-Lowry definition, and Lewis acid-base definition. So let's talk about the Arrhenius definition of acids. Acids, they release H plus ions or hydronium ions in solution. So that's the Arrhenius definition. Now keep in mind, in water, the H plus ions do not exist by themselves. Rather, they're associated with water to produce the hydronium ion, known as H3O+. The Arrhenius definition for bases is a base will release hydroxide ions in the solution. Examples of Arrhenius acids include HF, hydrofluoric acid, HCl, hydrochloric acid, H2SO4, sulfuric acid, HNO3, nitric acid. All of these acids have a hydrogen in front of them. So let's say if you put HCl in water. Hydrochloric acid will dissociate in water. It's going to donate a hydrogen to water, creating the hydronium ion, and also the conjugate base, chloride. So as you can see, an Arrhenius acid releases hydronium ions into the solution. Arrhenius bases include sodium hydroxide, potassium hydroxide, calcium hydroxide. Now let's say if you were to put sodium hydroxide in water, it's going to dissociate into sodium ions and hydroxide ions. So as we can see, this is an Arrhenius base because it releases hydroxide ions into the solution, which will cause the pH to increase, making the solution basic or alkaline. Now what about the Bronsted-Lowry definition of acids and bases? You need to know that a Bronsted-Lowry acid is basically a proton donor. An H plus ion is a proton. A Bronsted-Lowry base is a proton acceptor. Now let's consider the reaction between hydrofluoric acid, which is a weak acid, and water. So these two will react reversibly, producing H3O+ and fluoride. So as you can see, HF is considered an Arrhenius acid because it releases hydronium ions into the solution. But it's also considered a Bronsted-Lowry acid because it's a proton donor. HF lost a hydrogen. It donated a hydrogen to water. Because it lost the hydrogen, it is the Bronsted-Lowry acid. Now water was the proton acceptor. Water accepted the hydrogen as it turned into the hydronium ion. So water in this case is the Bronsted-Lowry base. The hydronium ion is the conjugate acid. Whenever you add a hydrogen to a molecule, you create a conjugate acid. Fluoride is the conjugate base. Whenever you take away a hydrogen, you create the conjugate base. So, for example, consider the bicarbonate ion, HCO3-. What is the conjugate acid and the conjugate base of this particular ion? Whenever you want to write the conjugate acid, increase the hydrogen number by 1. So if you add 1 to it, you're going to have 2 hydrogens total. Now, because hydrogen has a +1 charge, you need to increase the charge by 1. -1 + 1 is 0. Now, if you want to write the conjugate base of bicarbonate, take away a hydrogen, so it's going to be CO3, and decrease the charge by 1. -1 - 1 is -2. So let's do a few more examples writing conjugate acid base pairs. So let's try ammonia. What is the conjugate acid and the conjugate base of ammonia? So to write the conjugate acid, increase the hydrogen number by 1. Now the initial charge was 0. This is neutral. If we add 1 to it, it's going to have a +1 charge. For the conjugate base, we need to remove a hydrogen and decrease the charge by 1. 0 minus 1 is negative 1. So NH2 minus is the conjugate base of NH3. NH4 plus, ammonium, is the conjugate acid of it. Now what about this one? What is the conjugate acid and base of hydrogen or monohydrogen phosphate? Feel free to pause the video and work on that example. So to write the conjugate acid, let's increase the hydrogen number by 1. So it's going to be H2PO4. And increase the charge by 1. Negative 2 plus 1 is negative 1. For the conjugate base, we need to take away a hydrogen, so it's going to be PO4. And we need to decrease the charge by 1. Negative 2 minus 1 is negative 3. So that's how you can write the conjugate acid and base of any molecule or ion. So now let's get back to the Bronsted-Lowry definition of acids and bases. So consider this reaction. Let's say carbonate reacts with water to produce the bicarbonate ion and hydroxide. So which one is the Bronsted-Lowry acid and which one is the Bronsted-Lowry base? So bicarbonate accepted a hydrogen atom, or to be more precise, a hydrogen ion. It went from CO3 to HCO3. So because it accepted a hydrogen ion, it is the Bronsted-Lowry base. It is the proton acceptor. Now water released or gave away a hydrogen ion. It went from H2O to OH minus. So because water lost the hydrogen ion, it is the Bronsted-Lowry acid. Now if you go from water to hydroxide, it's a loss of a hydrogen, so therefore hydroxide must be the conjugate base, since it lost the hydrogen going from H2O to OH minus. Now carbonate, it gained a hydrogen. Whenever something gains a hydrogen ion, it becomes the conjugate acid. So bicarbonate is the conjugate acid of this reaction. Okay, so let's try a few more examples. Go ahead and determine which one is the Bronsted-Lowry base and which one is the Bronsted-Lowry acid. In addition, determine the conjugate acid and the conjugate base produced on the right. So let's start with the reaction on top. So going from NH3 to NH4, we can see that NH3 is the proton acceptor. It gained a hydrogen ion. So since it's the proton acceptor, it is the Bronsted-Lowry base, which means that NH4 plus is the conjugate acid, since it gained a hydrogen ion. Now water lost a hydrogen ion, which means water is the proton donor, which makes it the Bronsted-Lowry acid. And hydroxide, it lost a hydrogen ion going from water to OH minus, which means that it's the conjugate base. So let's do the same thing for the one below. Methanol lost a hydrogen, so it's the proton donor, so it's the Bronsted-Lowry acid. Water gained a hydrogen, so it's the Bronsted-Lowry base, which means that H3O plus is the conjugate acid, and methoxide is the conjugate base. Now let's go over the Lewis acid and Lewis base definition. So a Lewis acid is basically an electron pair acceptor. A Lewis base is an electron pair donor. A good example of a Lewis acid-base reaction is the one between BH3 and ammonia. Now ammonia, the nitrogen atom in ammonia, has 8 electrons around it. It has a lone pair and 3 bonds. Each bond equates to 2 electrons. So nitrogen doesn't have any space to receive electrons. However, it can donate a pair of electrons due to this lone pair. Now boron has an incomplete octet. It only has 3 bonds, 6 electrons. It can accept a pair of electrons, which makes boron the Lewis acid and the nitrogen in ammonia the Lewis base. So the nitrogen can donate a pair of electrons, or 2 electrons, to create a bond between boron and nitrogen. So therefore, because nitrogen donates the lone pair, it's the Lewis base. Because boron accepts the lone pair, it's the Lewis acid. So the product of this reaction looks like this. Whenever nitrogen has 4 bonds, it has a positive formal charge. And whenever boron has 4 bonds, it has a negative formal charge. Overall, it's still neutral. So that's an example of a Lewis acid-base reaction. The Lewis base is known as the nucleophile, which is electron-rich. The Lewis acid is the electrophile. It's electron-poor. It wants electrons.